talking about a a transmitting station, that means a computer, let us say, a transmitting computer and a receiving computer, right, connected with each other. There are three primary things that one has to take care. Number one is you have to make sure that the data that you have, whether it is in the form of digital data or whether it is in the form of analog data, has to be converted to the appropriate signal that is required to transmit the data through the channel. You have to convert it appropriately. So what does it mean? Let us say that if we are talking about the digital signals, transmission of the data in the form of digital signals, right? So the digital data has to be converted to digital signals for transmission through the digital medium, right? Through the medium. And if you are talking about analog data, right? So that analog data, let us say voice or something, right? So the analog data will also have to be converted in some way so that it can be sent as digital signal. So analog data has to be converted to digital signal, right, for sending through the transmission medium, which takes only digital signals. Likewise, instead of digital signals, if you think of the analog channel, right, where analog signals are only taken, if you have digital data, then it has to be converted to analog signals. If you have analog data, that also has to be converted appropriately to analog signals. So you have four combinations. You have digital data, you have analog data, you have digital signal, you have analog signal. So you have four combinations, right? Digital data, digital signal, digital data, analog signal, analog data, digital signal, analog data, analog signal, right? So this is very important. So you need to transmit the data, right? So far what we were considering, and in this course actually what we are restricting ourselves to is the transmission of digital data and analog data over digital medium. That means that digital channel. So that means that the signal has to be digital, right? And signal has to be sorry. So what did I tell? No. So we are talking about so we are talking about the digital data, right? So we are talking about the digital data, and that has to be sent over digital signal as a digital signal, or the digital data which has to be sent as analog signal, right? We are only considering these two. So so let us see how the digital data can be sent as digital signal, that we have already seen actually, and we'll also shortly we'll see that how the digital data can be sent as analog signal. The rest of the combinations we are not considering as part of this course. Okay, so we are restricting it out of the syllabus. So so far what you have learned, the line encoding schemes basically help you to convert the digital data into digital signals. So you have learned the unipolar schemes, right? So for example, unipolar inner Z, non-return to zero. Then you also have the polar schemes also, polar inner Z. Then you also have polar RZ, right, return to zero. Then you have among polar schemes, what are the other polar schemes? Can somebody tell me? The biphase schemes, right? Manchester and differential Manchester. Then you have you have separate bipolar. You have separate bipolar schemes, AMI and pseudo-ternary. There are few other schemes also that are there, like multi-level schemes and multi-transition schemes, which we are not covering, in this course. Okay, we are not covering in this course. So we are restricting to only these line encoding schemes. So line encoding schemes basically ensure that between the sender and the receiver, the digital data can be converted to digital signal appropriately. Now, we have also seen that the different types of line encoding schemes, there are different problems, right? Problems with respect to DC component, problems with respect to synchronization, and so on, right? So different schemes have different issues, right? Similarly, with respect to the data rate, signal rate, etc. So these schemes basically they have their own different characteristics, right? So and they are useful for different types of communication. So it's not like only one type is useful, the other types are not. It's not like that. They all have their own different places of implementation. Okay. So so this is this thing. So now let us try to understand that what is there beyond line encoding, what we have covered in the last class. So that is called block coding. Okay. So now block coding basically takes care of the fact that there might be errors that can creep in the process of transmission, right? So we will cover tomorrow how to detect these errors. It is called error detection. We'll cover tomorrow how to detect the errors through mechanisms called error detection. There are also mechanisms for error correction, but that is more computationally expensive, and also it is more complex. So error correction mechanisms, we are at the physical layer, we are basically keeping out of scope from this course. So we will restrict to only error detection. Now for error detection or for the synchronization aspect that we have discussed in the last class, whether for synchronization or for the error detection, you need some extra bits. You need some redundancy. You need to add some extra bits to the original data bits that contain the actual data. So you need to add some extra bits, right? So this basically is useful to resolve the issues of error detection, and also it can take care of synchronization to some extent, right? So how is it done? So it is done with the help of something called block coding. Okay, so block coding basically will give a code that can help in error detection, and also it will aid in synchronization. So we have seen that synchronization problems can happen due to let us say you have a number of signal level remaining the same at certain voltage, etc. So like that, so for that actually synchronization can happen. So like that actually there are many other issues also. We are not getting into it in the interest of time, but let us try to have a look at this picture that you see in front of you, right? So in block coding, the first step that has to be done is called division. Okay, so you have this bit stream. Let us say that you have a continuous set of bits, right? So you take one block of bits, right? So what you have to do is you have to take the block of bits, and then you have to group them into m bit blocks. So every block has m bits. So m bit blocks will be produced through the division process in block coding. After that comes the substitution process. So in the substitution process, what you take is you take each of the m bits and you substitute with an n bit. You take the m bit and you substitute with the n bits. So that means that you are adding some redundant bits. Basically, you are adding some redundant bits in a certain way. Okay, so we have to add some redundant bits. Okay, now so what we will get at the end of this, you will get n bits, substituted. So substituted m bits to form n bits, right? So n bit blocks like this. So then you have to combine these n bit groups to form the stream, to form the entire stream that has to be transmitted. Okay. Now this resultant bit stream basically prevents certain bit combinations that, when used with line encoding, would result in the DC components or poor synchronization quality. So it can resolve these issues of DC component and poor synchronization issues, right? So let us try to have a look through some of these block encoding schemes. So the first one, which is very basic, is called 4B5B. 4B5B scheme. So with a slash, 4B5B. Now, so you have a look at this particular scheme. So in 4B5B, initially you input the bit sequence. You take the input bit sequence and you group into 4-bit groups, right? So the m over here is 4. The m over here is 4, and then you substitute, make the substitution, and you create the 5-bit groups. That means n over here is going to be 5 as per a certain mapping scheme. Now this mapping scheme for 4b 5b is already predefined, and it is given in your book in table number 4.2 in Foruzen, right? So it is there. If you have the 5th edition, it is table 4.2. If you have a previous edition, it is going to be different. So you have to check, so what is the corresponding table. So 5b 4b 5b mapping scheme will be used in order to map the data sequence to the encoded sequence, m bit, that means 4-bit, to the 5-bit. So how this mapping is going to be done? That will be done as per the mapping table. Now in this mapping table, as it happens, okay, you have some control characters also. That is, apart from data characters, you can have some control characters. So these control characters are going to be encoded again with some 5-bit sequence. So not only the data, actual data, but also some control characters are also going to be encoded with the help of this 5-bit sequence. Okay. So you see that what we are doing, we are taking 4-bit groups and we are encoding into 5-bit groups. So basically, a group of 4 bits, you can have, with a group of 4 bits, you can have 16 different combinations, while a group of 5 bits can have 32 different combinations. So this means that there are 16 groups that are not going to be used for this 4b 5b encoding, right? And some of these unused groups are basically used for this control sequencing that I was telling you. And the others, the rest of the others are not going to be used at all. So this is basically how it is done, right? Now you have a look. Then what 4b 5b does is that you encode, right? And then you use some appropriate mechanism, let us say NRZ I, the inverted version of NRZ, right? You take the appropriate encoding scheme and then you encode and you send to the other side. So this NRZ I encoding and decoding will be done, and then it will be sent to the 4b 5b decoding block for the further decoding part. So at the gross level, basically, this is how it works. Okay. Now you see that NRZ I basically offers better signal rate compared to biphase schemes. So the signal rate is 1/2 of biphase schemes, but it suffers from synchronization. So the synchronization issue basically with 4b 5b will be taken care of. So if you are talking about NRZ I scheme, you can resolve the synchronization issue. You can take care of it by integrating it with the 4b 5b encoding decoding scheme. Okay. So similar to 4b 5b, there is another one which is called 8b 10b. 8b 10b. Now this 8b 10b, basically here also the purpose is the same, and you do exactly whatever I told you earlier. But here basically what you do is you break the you break the 8-bit block into 2 blocks. One is 5b, the other one is 3b. Okay, so 5b 3b, so together you get 8b. So 8b will be so the 8b block basically is going to be broken in this manner, and then ultimately you are going to get, after substitution etc., you are going to get 6b plus 4b equal to 10b. So you are going to get a 10b block. Okay, so then basically the 10b is going to be amalgamated with all these 10b blocks, and basically so it is going to be transmitted. Okay, now so that is basically answer. Now the problem with block encoding, it is good. It resolves some of the issues with the regular line encoding schemes. But the problem is that block encoding has to be done separately, right? So to address this additional step, not to have an additional step, scrambling basically can be used, where as opposed to block encoding, it can be done at the same time with the same purpose. However, in scrambling, you do not really need to introduce any extra bits for the purpose. The objective is basically to replace the long sequence of zeros and ones with some predefined bit sequences to improve synchronization. Now, this particular sentence is the heart of scrambling. So let me read this sentence once again. This is the whole idea, this is the whole objective of scrambling, that scrambling basically intends to replace the long sequence of zeros and ones, which basically is a problem in line encoding, right? So the long sequence of zeros and ones will be replaced with some predefined bit sequences to improve the synchronization problem. So synchronization is a problem. Synchronization happens due to this occurrence of these long sequences, and then these long sequences are going to be replaced appropriately with some substitute sequence which is predefined. Now this is what scrambling is all about. Now this scrambling basically, because you are not introducing any further additional bits, scrambling does not change the bit rate, and it maintains the DC balance by balancing the positive and negative voltage levels. How it is done, I'm going to show you shortly. So scrambling is not going to introduce any further additional voltage level, right? If you are adding some, the substitute sequence is such that if you are adding a positive voltage, it is going to be neutralized in the next bit with the negative voltage level. So there are two different scrambling techniques. I'm going to highlight these two. So the first one is called the B8ZS, B8ZS, and the second one is called HDB3. So first, let us look at the B8ZS technique. So the full form of B8ZS is bipolar with 8-0 substitution. Bipolar with 8-0 substitution. Now this particular scheme is used in North America. The other scheme that I told you, which is HDB3, is used in the rest of the countries, most of the rest of the countries, right? So B8ZS is mostly used in North American communication systems, which basically talks about replacing a sequence of 8 zeros by a bit pattern, which is this predefined bit pattern, which is 000 V B 0 V B. So if you encounter 8 zeros, right? If you encounter 8 zeros, you replace that sequence with this pattern 000 V B 0 V B. This is the pattern. Now let us have a look at this sequence. Okay, so let us say that we have 8 zeros like this. After 1, there are 8 zeros. So these 8 zeros are going to be replaced with 000 V B 0 V B. Now it might occur in your mind that what is this V and B? Zeros I understand, but what is V, what is B? So V is called the violation bit, whereas B is called the bipolar bit. So violation bit basically is introduced in order to set the violation. So whenever some 3 zeros occur, the computer basically introduces this violation bit. It says that okay, enough, I don't need any further zeros. So violation, there will be a violation. Okay, so now once this violation is introduced, right, it will have some voltage, positive or negative, whatever it is. So that has to be balanced. So for balancing that, you need to use this B bit. Okay, so you see the rule is like this, that if the previous non-zero bit is positive, then you get a positive violation. Because you get a positive violation, now it is now polar. So the polarity is positive, right? So because the polarity is positive, with the B bit you neutralize the polarity, which will neutralize, right? So this is positive, so you make it negative. Okay. So if the previous bit level is positive, that means over here this previous bit level was positive, so you introduce this. If the previous bit level is negative like this, then the violation bit will have negative V. If the previous level is positive, like in here, the violation bit will be positive. The violation voltage level corresponding to this bit is going to be positive. Whereas if the previous level is negative, right, then the violation bit is going to be negative like this, and then you use the bipolar bit like this to neutralize it. And because of this, again, so the rest of the sequence is going to continue. Clear? So we have, this is B8ZS. Another type of scrambling technique, which is also very common but is used grossly outside of North America, is called HDB3, high density bipolar 30. High density bipolar 30. So here it is even simpler. So here basically what it is saying is that if you encounter 4 consecutive 0 level voltages, those are going to be replaced with a sequence of 000 V if number of non-zero pulses after last substitution is odd, and if the number of non-zero pulses after last substitution is even, then you replace with this sequence. So here it is even. Okay, so you are going to replace with so number of non-zero pulses after last substitution is even, so you are going to replace with B00V, and then again you check over here. If it is odd, you replace with 30V. Again it is even, you replace with B00V. So here you are considering 4 bits consecutively, and then you are substituting with this corresponding scrambled sequence. This is called bit scrambling. So the first one was B8ZS, the next one is HDB3. So those were basically how you are going to send the digital data as digital signals. Now analog data can also be sent as digital signals, for which you need to convert the analog data to digital, right? And a digital signal is superior to an analog signal because it is more robust to noise, right? And that we know, right? That is the advantage of digital signal over analog signal, that it is more robust to noise and can easily be recovered, corrected, amplified with the help of various techniques like the ones that we are learning over here. So for this reason, nowadays the tendency is to basically send analog signals also as digital data. Is to change an analog signal to digital data. Yeah, that's correct. So analog signal also to digital data, right? So that is the analog to digital conversion, which we are going to cover shortly. So any question you have before we move to the next topic?